So as I was saying, before we start with talking with the topic, I want to just give you a quick overview about what it is Ericsson right now and what we are doing overall. So as you see, there are many things here, and the repeating words is probably network. So Ericsson was at the beginning a company which was working with radio access network. So anything that has to do with the mobile phones network, let's say. And they do still do that. So they give elements for the part of the radio and other hardware boxes that are needed for making sure that your local and regional areas are covered by mobile data and networking. However, they do other things. We do other things. We have also many software-based services, and we work in many different scenarios and use cases that are, we say, vertical. So they are not only about the lower part of the network and this kind of things that are more like engineeristic, but there is also a lot of things that we do in the software field, in the computer science field. For instance, if you watch the latest Winter Olympics, Ericsson was part of the group that made it possible to have that cool stadium in which everybody had tablets and they were able to visualize in real time the player in the field with all the statistics of them, bracket it around them, following them where they were going around. Or when they were skiing, there was that perfect moment in which they were able to do a 360 degrees videos in real time all the time of the ski play guys, and you could see it from whatever angle you liked. So all of this cool stuff actually relay on the mobile network somehow. That is true. So I think we will start by talking about that. And then today I will mention to you one of the experiments we did within Ericsson and ELTE, so with the bachelor and master students as well, which was revolving around AI and this kind of content. So let's start by talking about what it is our typical network nowadays. So how does your phone connect with the rest of the internet and whatnot? So maybe some of you are familiar with this. So you know that there are towers and your phone is connecting via radio. So there is this connection that can come and go, and oh my God, my phone doesn't take anything here, but then it will work 5 minutes later, 2 steps ahead, because we're working with radio waves, right? But then from the radio station on, we have a big bunch of components, of boxes, of hardwares that connect local area to regional area to very far away infrastructure, which is usually data center from your mobile operator, where you will have all the parts of the logics that helps the whole system works. So for instance, here you will have things like a database that tells them, hey, this guy is a telecom guy, so he has access to X amount of data and this much of bandwidth and whatnot. And then from there, we also have the connection with the rest of the world, with the internet, right? So when you're using your data, what is happening is that the information from you to the cloud is traveling all around this line very far away, more than 500 kilometers sometimes, and then back towards the same way to you, which is quite the long way, yeah, right? In fact, if you think of this, you can see that if you are in Sopron, for instance, and you are trying to watch a Netflix movie, or if you're trying to access a service on a Google Cloud, what is happening is that you not only have a big delay that is caused by the fact that you are physically distant from these guys, from the Budapest data centers, where your operator, where when T-Mobile or whoever is doing the handling of your calls and whatnot, but you are even farther from where the actual service is staying. So for instance, the video, the game or whatnot is on the North Pole somewhere very far. How does this translate to what we do nowadays in Ericsson and within the research at ELTE? We are trying to cut this distance. So if the problem is that we are too far, so our little electrons and our signals have to travel too long, too much along the line, we can save time and have cool application, real-time things that happens, a lot of multiplayer games in real time with you that are projected in super three-dimensional cool worlds or whatnot, by just moving all the information that are needed a bit closer. This sounds very obvious and simple, but it becomes very complicated because it's something which was already there. You know, this kind of networks were like this for many years, and it's very complicated to decide what should be that is so important and has to be close to us so that we can access it immediately, and what will be instead staying far away in the North Pole in the fresh data centers of Google. And the technology that is working with this kind of mentality, it's called edge computing. So the idea that you have a computer or a database a bit smaller, but on the edge of the network. So in Budapest, so that you can access it closer from Sopron, if we go back from the previous example, right? So why this becomes useful? If we do a very little physics and math here, you know, when we are moving signals, when we are moving data, we are moving at least with the same speed of the light. We are, of course, that is actually slower than that, but electrons in the void will move with at least that speed. So it's like 3.3, right, or something like that. So if we count the fact that we have a physical barrier, we have our optical fiber cables that connect our antennas to the rest of all the logic that I told you is inside this complicated network. You see that this 500 kilometers translate in a delay which is higher, of course, than the 3.3 microseconds we would have per kilometers in the void. This will come up to something like 5 milliseconds probably from here to here or something like that. And then you see that because the human eyes is able to perceive up to 24, 25 milliseconds distance between one frame and another of a video or something like that, then you see that we are already stealing a lot of time from the actual game to happen, for the actual logic of the game to go. And we have less and less time for, so that the user at the end will kind of notice that something is wrong, that we are too slow and it is not nice to play this game, which is in the North Pole. So instead of having all this way up to here, what we are doing now is that we are doing up until Budapest and back only, which is way less kilometers, and it means way less work, way less weight for us that we are using the network. How does this come to the play with AI? I will tell you by describing what was the scenario we had in the lab between the Ericsson and the Elte. So what we had was this beautiful setup in which we said, okay, how smart can we be? So how much can we use a computer to, for instance, take life and death decisions? So let's have a simple simulation of it, of course. Let's not kill anybody, but let's try to see if we are fast enough with very small amount of data, just by the fact that instead of using very far away cloud, we are using instead an edge computer. So we had 4 cameras, which give us fixed video streams of a scene. And this scene was a simple train running on a track. And the idea was we had these little puppets and we were training the system to recognize them. So that, hey, if there is a rock here and the train is going, nevertheless, it can go. But if one of these guys crosses, we want the train to stop immediately. So it's pretty common scenario. We want to have a computer deciding whether or not a human is crossing the street, not by having a camera on the train, but by having fixed cameras. How does this work in the background? So in the cloud, we had something that is called training of an artificial neural network. I don't know if you are familiar with this, but basically the idea is that we are trying to simulate what your brain does. So what we do is that we collect a big bunch of images, for instance, the puppet of the cat and the puppet of a dog, and we label them. So we say, okay, this is a cat, this is a dog, this is, I don't know, Anna crossing the street. And we feed these images to what we call neurons, so that every little pixel that composes the image will be owned by a neuron. And these neurons will then be going through a bunch of hidden layers, hidden steps, in which basically we are just deciding with numbers, with weights, whether or not this pixel is important to understand what kind of picture is that. So for instance, okay, I know this pixel and this pixel in this specific position usually should be the eyes, and thus if they are this color, then it's a cat, or if they are this shape or whatnot. Of course, I am simplifying here. And then the output would be a decision, so a filtering based on these thresholds that we are creating, whether or not the image that we are seeing right now is a cat or a dog, for instance, a Chihuahua. And of course, at the very beginning, when you are doing this training, the whole thing will be very bad, extremely bad, and will always have errors. But because we have the possibility to know that there are mistakes, because we have labeled this input data, then we have reverse feedback inside here where we can change the error that we are making. We can change the weights that we give to each of the pixels so that the decision the next time can be better and we can recognize cats for cats. This becomes very tricky things to do in real life because these kind of systems are very good for specific things. So you can train them very well for the same kind of inputs, but as long as you go slightly different or slightly out of context, then they are not good anymore. So it is very difficult to realize these things that, you know, your life is depending on it and you have to be able to trust it. You don't want for a Chihuahua maybe to be crossed up by a train, but it's fine if there is a muffin there, right? How does everything come back to the whole use case? So how did we do everything? So we started by having these recordings of the whole track and the person moving, the little man moving, and then a cat, and then whatnot. And we extract the images from the video recordings. And then we had to manually label them. So this is the boring part. This is the part that takes a lot of human effort and a lot of time. But after that, then there was the part which is the learning, which is this whole process that I've explained, right? So this whole, okay, let's take the image and split it and give weights and try and again and again. This part takes a lot of computation. So it needs big computers, it needs a lot of time, and this can be done in the cloud. So that stayed in the cloud in our simulation. However, after we have learned, what we have learned actually is very simple because it's just thresholds. It's just numbers that tell us, okay, this is good, this is not. So we vote that this is a cat. And this part can stay in the edge. This part can actually be a very small amount of information that are needed. And the logic of the decision can be taken now very close to the user, can be taken in Budapest and brought back to Sopron like this. And then finally, what we had at the very edge of the network, so on your tablet, when you were looking at the scene rendered by the 4 cameras, was all the logic behind all the images that you can add up. So for instance, we had the bracketing of a square, we were putting the names next to it, okay, stop train, the train would stop and whatnot. So this part, of course, and the video itself feeds the cameras were on the place where the things was happening. And so we basically did what I told you before. So we had finally a simulation of an AI application, which was running on the edge very quickly in time to stop the train. And we had our stupid puppets being stopped by the stopping it by the simple fact of crossing there. And in the meantime, the database with all the images and the whole big training was done in the cloud, offline at the beginning. And also, potentially what can happen now is that every time we make a decision, this decision will be either good or bad according to what is the outcome. So if there is no accident, if the train does not crash or nothing else, we consider it a good decision. And that can go and increment the amount of knowledge we have in the training. And that will move on towards another kind of machine learning. So I'm diverging here. But yeah, so overall, you see all of these new things, new technology putting together to make this kind of new application. I think the presentation is finished here. I wanted to probably mention that during the project we have multiple amount of students collaborating, doing everybody a different thing. There was somebody that was playing with making the Android application on the tablet, somebody that was trying to figure out how to do the streaming with the cameras, and somebody else was trying to figure out what was the best algorithm for the compression of the video and whatnot. And the whole thing was an effort of probably a team of around 7 or more people. And among those, we had, of course, guides from Ericsson. So we had some supervisor from Ericsson, which was involved in the whole project. And we had professors and PhD students, master students, and bachelor students. So this is just one of the millions of examples you probably heard today of what kind of professional experience you can have meanwhile you are studying at ELTE. And this is the kind of thing we do every day in Ericsson in the research area. So we have toy cars and toy trains and whatnot, and we just play and experiment with them for this. I don't know if you have questions for me, if you like. You can even write them in the chat. If you're curious about anything, I can answer you back. Otherwise, we can end the meeting here and you can join some other presentation. It was a pleasure to talk with you. And any kind of question you have about the experience, the international relation of ELTE or Ericsson or whatnot, I will be happy to answer.